Hello folks, Phil Truby here. When I heard about the Cybertruck, the first thing I tried to do was to learn about this mysterious Etherloop network that Tesla supposedly invented. So I started pulling on that string and it led me down a rabbit hole of advanced technologies. Let's dive into what I found. First, let's contrast what Tesla has done with almost every other car in existence. This is a highly simplified diagram of what one electronic control unit, or ECU, does in a regular car. This is the body controller, and it controls all the lights, switches, windows, seats, locks, door releases, wipers, column stalks. All this is done in a single printed circuit board with a microcontroller, and to do all this, it has to have lots and lots of cross-body wiring. These wires have to go across the body all to a centralized body control unit. And each ECU is like this. The tire pressure management system has to be connected to sensors near each wheel, which results in more cross-car wiring. Regular cars have about 70 ECUs. Car manufacturers buy these ECUs as black boxes. The ECU does its job, be it braking, steering, engine control, ABS braking, or traction control, all largely independent of each other. Both the sensors and the outputs are connected to the appropriate ECU, so all a car manufacturer has to do is to buy an entire brake system, for instance from Brembo or whoever, and the integrated ECU comes with it. So along with the problem of cross-car wiring, another problem with this architecture is upgradability. There's typically no mechanism to do an over-the-air update. Okay, so what does Tesla do different? Well, instead of 70 ECUs spread around the car and associated cross-car wiring going to many of them, Tesla instead has 6 master controllers, also known as zone controllers, which are placed in strategic locations, such as the left front, central MCU, right controller, rear controller. And there's a couple of other important ones, the high voltage controller and the autopilot. Each of these controllers is connected via an Etherloop network. This is high-speed Ethernet, and I'll get into the specifics of what kind of Ethernet Tesla actually uses a little bit later. So, unlike a regular car with a single body controller that is wired to each switch and motor in each door, Tesla further delegates processing to subcontrollers. So in this case, there's a trailer subcontroller and a door subcontroller for each door. So for each door, you'll have lighting, switches, window and mirror motors, maybe airbags, locks, and proximity sensors. All this control and sensor wiring is contained within this single door controller. And with just a single twisted pair CAN bus wire going to the nearest zone controller. CAN bus can be used for communication to these subcontrollers since the data requirements are minimal, and CAN bus is a lot cheaper than Ethernet. You can buy automotive-grade microcontroller chips with built-in CAN bus communication links right on the same chip. So Ethernet is only used when they need it for high-speed communications and fault tolerance, and more on that later. The title says that Tesla both centralizes and decentralizes control. So what do I mean by that? Well, first, the 6 main controllers handle everything. Look at this not at all comprehensive list of things that the controllers handle. I actually ran out of room to list them all. Speakers, wheel sensors, motor functions, steering, HVAC, and so on. Each of these left, right, and rear controllers is a single printed circuit board with a single CPU. So, for instance, the speakers near the left controller are controlled by the left controller. The left controller has audio amps and directly drive the nearby woofers and tweeters. Same goes for the right and rear controllers. But think about what that implies. Audio functionality, which is a single system, I mean, all speakers had better be playing the same thing, right? Audio functionality is distributed among the many zone controllers, and this is done for everything. Wheel sensors, various motors, inverters, and stuff. So this isn't one microcontroller running a simple program as you'd find in a normal car ECU. This is actually a distributed multi-processor operating system split among the 6 zone controllers, which are all connected via Ethernet. This is pretty complex stuff. Somehow, the speaker outputs have to be routed to each zone controller, while each controller is also monitoring wheel sensors, giving driving inputs, running the HVAC, all simultaneously while keeping each controller updated about what is going on in their zone. The technological sophistication of the code running on each zone controller is immense. Frankly, I'm not surprised that Volkswagen can't figure this out, and this is the reason they partnered with Rivian, because Rivian is the only other manufacturer that I know of that does a zone control system like this. This is more advanced computer programming than what 90% of Microsoft does, which is a software company. Application programming like Excel is simple in comparison architecturally to this. So you can see why gigabit Ethernet is critical for communication between the various zone controllers, since they all have to be in sync, controlling each individual wheel or motor while blasting highway to hell on 20 speakers. In fact, Tesla came up with their own communication protocol riding on top of Ethernet for this. This is yet another unique Tesla communication protocol. They built a fast, low-latency protocol for their AI supercomputer, Dojo, and then this protocol, which I'll talk about in a couple more slides, is called Etherloop. Now, Etherloop is different in that it has to be both deterministic to sync up all the controllers and fault-tolerant in case one of the links goes down. The main controllers are connected in a loop, so data can flow backwards if a link goes down. Now, even with Tesla's zonal architecture, which drastically reduces cross-car wiring, don't think it is all super simple and elegant. Cars are really complicated and still require a lot of power and signal wiring. This is the Cybertruck's rear controller board showing all the wiring leaving it. You've got this mess of wires right here. You've got another wiring bundle here. You've got ribbon cables with tons of signal coming out here, and another here as well. Before I show you some details about the Tesla Etherloop protocol, let me show you another electrical innovation that Tesla has been using in all their cars for many years. This is a typical automotive fuse box. Every 12-volt electrical load in this car is centralized through one of these fuses. This is actually for an AV, as a matter of fact, the Ford Lightning to be specific. And here's another EV. This is for GM's Lyriq EV. And here is Tesla's fuse box. The best part is no part, and Tesla hasn't been using fuses for a very long time. Instead of fuses in a fuse box, Tesla uses power MOSFET chips. You can think of these chips like a solid-state relay or a switch. They are, in fact, a very low voltage drop transistor. Your source power comes in one pin and it goes out of another pin, and then a third gate pin is used to turn the power on or off. So this is a very simple high amperage semiconductor switch. Here's how it works. Input power, 12 volts or 48 volts or whatever, is fed into the input pin of the MOSFET. There is a very simple circuit which monitors the current that is being drawn by the load at any one point in time. If that current gets very high, so like in a dead short situation, it would immediately, this current sensor, which is a very simple circuit, would immediately send a signal to the MOSFET to cut the load. This short trip, if you will, can happen in microseconds. This is in comparison to a typical fuse. And the way a typical fuse works is that you have a thin wire within the fuse, like right here. And in a dead short situation, what has to happen is that the heat has to build up high enough so that it literally burns out this wire, and then the fuse is blown after that. This current sensing circuit for a dead short can happen in microseconds versus milliseconds or more, maybe seconds even, for a fuse. The other thing that happens is that the current sensor also reports the value of the current that is being drawn by the load to the CPU. So this provides a lot of interesting capabilities. One of the things you can do is you can have variable current graphs basically within the CPU. Let's say you're turning on a motor. When you turn on a motor, typically it draws a lot of current for a second or two as it starts up, and then it reduces that load quite a bit after that. So the CPU can actually monitor that, and it can allow the current to be high at the beginning, but after a few seconds of the motor running, it can tighten up its tolerances quite a bit. The other thing that's really interesting about this is that the CPU can monitor current over time. So let's say we have a wiper motor, for instance. When it's brand new, the wiper motor is drawing a certain amount of power whenever it operates. But over time, maybe its bearings are starting to get worn, and it's using more and more and more power. Well, the CPU can monitor this, and it can the current might not get to a point where it would trip and turn off the power, but the CPU can say, hey, we're using twice the amount of current that we used to 2 years ago. So it'll hit a maintenance threshold, and the CPU can then inform the user or inform Tesla that the motor is getting old or the component is getting old and needs to be replaced. So this ends up being a way of having advanced diagnostics and maintenance. The other thing that this circuit does, of course, is that you have far less wiring. So no central fuse box is needed. These circuits go on every zone controller. So it's distributed again throughout the car. Here's a picture of the Model 3 front zone control board from a few years ago. These little chips right here are the on-off MOSFET switches. Looking at this board, it kind of begs a question. Why the heck is Tesla complicating its life with such complex circuit boards, a distributed multiprocessor real-time operating system, E-fuses using these fancy chips? Why is it doing all this stuff? Well, it isn't just trying to be the smart-ass, cleverest kid in school. This is actually reducing manufacturing cost by speeding up manufacturing. These boards look complicated, and they are, but they are built in a high-volume, completely automated manufacturing line. The software is complex, but that's a one-time cost. And out of all this, they get a much simpler wire harness, which also speeds up manufacturing time. And while I don't know this for sure, I'm pretty sure that Tesla started down this whole road with a vision of a fully automated assembly process, like their unboxed process. And they had this vision right from the get-go. To do unboxed, you've got to have a fully distributed zonal architecture. Without a full zonal architecture, the wiring will make the unboxed process very complicated, and it might not work without it. So they had to distribute these E-fuses throughout the zone controllers, which also happens to give them tons of secondary benefits as well. Since these cars are so well instrumented, they have tons of data to use when designing car upgrades. This CPU records so much information about what is working and what is not at the very detailed current load level that this info is used by engineers when they are upgrading components throughout the car. This is all info that used to be locked away within third-party ECUs, and only Tesla has access to it. Okay, finally, Etherloop. What is it? Well, Etherloop, first of all, is not your regular home Ethernet that we are all familiar with RJ45 jacks. It uses Cat5 or Cat6 cable, which is, by the way, a 4 twisted pair cable. Etherloop uses a different Ethernet standard called 1000 base T1 or 802.3 BP. It's been around and standardized, and chip manufacturers like Marvell make chips for it. There are actually a whole bunch of different Ethernet standards. So when people say Ethernet, you really have to ask them what kind of Ethernet are you really talking about? And this is an example of two Ethernet standards which are quite different. Anyway, 1000 base T1 or 802.3 BP uses a completely different connector, and the connector is called HMTD. They use a completely different connector because it has to be able to withstand huge vibrations, extreme temperatures, and be impervious to snow, ice, water, oil, and whatever else a car encounters. This standard does run at gigabit as well, but since it only uses a single pair of wires, the maximum length of each run is a much shorter 15 meters versus 100 meters for our normal home and office wiring Ethernet. Remember that amazing Monroe Live video with 5 Tesla executives, including Lars? When they pointed out the Etherloop socket, here in blue, it's the female version of the connector that was on the previous page, Sandy Monroe said that it didn't look like Ethernet, and the Tesla engineer said, no, it's a standard Ethernet connector. I thought this was all pretty funny because both were right. They just had different Ethernet standards in mind. By the way, this block up here, right here, is something called a switch tank converter, which is of course, cutting edge. Why wouldn't it be with Tesla? Cutting edge circuit to convert 48 volts to 16 volts at like 98% efficiency. It uses very little real estate, very little component cost, and it has massive efficiency for doing DC to DC conversion. Remember that this one board, and this is the left controller, this one board has speaker amplifiers. It has PWM controllers to control motors directly. It has power conversion. It has all the E-fuses for all the circuits that it's controlling, and tons of sensor communication for input. These are the headers for all the input and output pins for sensors and power. This is amazing density. This board does one heck of a lot of stuff. Another thing I'll add about Etherloop, remember the diagram I had about the Etherloop connections way at the beginning? This is the left controller, and the left controller was connected to 2 other zone controllers. It was connected to the central one and connected to the rear controller. But there's only one HTMTD connection. There's only one Etherloop. I'll just call it Etherloop. There's only one Etherloop connector on this board, so what gives? Well, Tesla optimized things again by simply using a shielded twisted pair wiring going out of one of these pins right here when it has to go from this left controller to the central controller. So it just used a shielded twisted pair wire, didn't use a complicated connection like this. When going across the car, when going from the front of the car all the way to the back, that's when they use the much more complicated HMTD connector. presumably because the distance is so much longer and there might be electrical noise and other vibrational issues to deal with. But where they can get away with it, they just use simple twisted pair wiring off one of these connectors to hop from board to board. Okay, so Tesla's Etherloop uses an IEEE standard for the physical layer, the automotive Ethernet. But technically, the word Etherloop refers to the transport protocol that rides on top of this Ethernet physical layer. Tesla's Etherloop is a transport protocol that provides deterministic packet travel between the controllers. It uses time-sliced windows to transmit packets. It is also link fault tolerant. If one of the controller links goes down, data will be routed in the opposite direction since all the main controllers are connected together in a loop. By the way, Etherloop is not used for the FSD cameras. Those have coax cable connections directly to the autopilot controller. Etherloop is also quite different from the Tesla Transport Protocol over Ethernet that the Dojo supercomputer uses for FSD training. So this is a second Tesla-created communication protocol, and this one is proprietary. Tesla has not published the protocol. So it's a transport protocol. It provides error correction, retransmit, and deterministic packet transfer. By the way, if you do a search for the word Etherloop, you might find a protocol that was invented in the 1990s. Which is quite different from this and has nothing to do with Tesla's Etherloop. So Etherloop is only used where it's needed, when connecting the main controller boards that have to act as one coordinated computer. CAN bus is still widely used. It is a much cheaper and simpler protocol, especially considering that the circuitry for it is built into a number of microcontrollers. Ethernet is much more complex and requires its own dedicated chip. Of course, CAN bus runs 200 times slower than automotive Ethernet, so the appropriate technology is matched to the right use case. Automotive Ethernet also does not support power delivery like our normal home Ethernet does. This actually makes sense since power delivery in a car usually isn't used to power a circuit board, but is much more often powering a dumb device directly, like a light or a motor. So it makes sense to have separate power wires going to these devices, and it also allows Tesla to incorporate eFuse circuitry into those power lines. Finally, while 48-volt power is a Cybertruck innovation, it is again only used where it makes sense, usually for high-power components like the steer-by-wire motors. One more thing. Tesla has actually published the wiring diagram for the Cybertruck, all 46 pages of it. I used it a lot in my research. I'll leave a link to this wiring diagram on the platforms this is published to. Okay, so that's it for this video presentation. Hope you found it interesting. Let me know if you have any questions and I'll try to answer them. Thanks.